Right, any discussion of probability is going to eventually turn to a discussion of Bernoulli and DeMoivre. So let's go ahead and turn to them and talk about implications of that. Bernoulli's theorem is what we know of as the notion of in the long run, or the law of large numbers. And what it refers to is this theory that as the number of times an experiment is performed approaches infinity or becomes large, the true probability of any outcome equals the relative frequency. This is sometimes called the frequentist view of probability. That is, the law of large numbers says that the larger the number of times we do an experiment, the closer the relative frequency is going to come to the real probability. So for example, if we were to flip a coin repeatedly, do a series of Bernoulli half-trials or perform a Bernoulli experiment, the proportion of heads will approach the true probability of 0.5. So to illustrate that, let me go to Excel and show you what I have here. I've written a macro that will flip a coin for me any number of times that I want to do it. So I might put in 5 here. If the probability of heads is 0.5, and if I click on this, it will flip a coin 5 times. And it'll tell me that it got a tails in the first flip, a heads, a heads, a heads, a heads. And then it will also, what it will do is calculate the relative frequency. So 1, 2, 3, 4 heads out of 5 flips equals a relative frequency of 0.8. We think that relative frequency and probability are very close to one another. We think that in the long run, relative frequency will equal probability. At 5 flips, relative frequency is kind of close to probability, but not really. We can see that there's a discrepancy of 0.3 between probability and relative frequency when we do this. Now if we did it again, you can see now I have a different set of outcomes. Heads, tails, 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 tails. I still have a discrepancy of 0.3, relative frequency of 0.2 now. This is just 1 out of 5 heads. And the nice thing about this little program here, this is called a macro, and I've added a button to my Excel book. I told you Excel does some awesome things. This is one of them, and it does. I can repeatedly do this experiment. And what you can see is that each time I'm getting a slightly different relative frequency. You can see that the flips over here are changing each time that I run this. I'm getting a different outcome. But as you can see, 0.1, 0.3, 0.1, 0.3, 0.1, 0.1, 0.3. The discrepancy tends to be pretty large. If I do 10 trials, we see that in that case the discrepancy is 0, 0.1, 0.3, 0, 0.1. If I increase this to 100, we start to see that the discrepancy goes down, that this relative frequency starts to get closer and closer to, if I change this to 150, you can see that now we are getting closer and closer. If I add this to 200, if I increase this to 300, if I increase this to 400, you can see that the discrepancy, as we get larger, the discrepancy becomes smaller and smaller each time we run this. We can go to 10,000. So in the long run, we're getting closer and closer. And what we think is happening, let's see if it'll run 100,000 times for us. You can see that it is very small. So as the number of trials increases from 10 to 100 to 1,000 to 10,000, we get closer and closer to, well, relative frequency equaling probability. So hopefully that illustrates the Bernoulli theorem. Now, let's say that we do an experiment where we flip a coin, say 25 times. But let's say we do this experiment over and over and over again. Now, sometimes we would get 10 heads out of 25, sometimes we get 11, 12, 15, 4, and so on and so forth. What if we were to then do that in Excel? So let's say we do this, and we do it 0.52, 0.44, 0.44, 0.68, 0.56, 0.52, 0.36. What if we were to start recording all of these relative frequencies? And then do that. Well, this is what DeMoivre's theorem is all about, is that if we were to take 25 trials, and let's say we were going to do, this is a coin, the probability of a heads is 0.5, and let's say we were to do this 100 times, and let's say we did the experiment and then we counted the proportion, the different proportions. This is the sort of result we would wind up with. This is the relative frequencies of the proportions. So if I take these proportions, and there are 100 of them, you see that? There are 100 of them. If I now make a relative frequency distribution of those outcomes, this is what I get. The mean of that distribution is 0.4868. I can do this again. I can do this again. I can do this again. Now this isn't just flipping the coin 25 times. It's flipping the coin 25 times 100 times. If we were to change this to 1,000, what would happen? 1,200. So what you can see is a characteristic shape here. Let's change this back to 100. Let's change this to 10. You can see that there's a lot of variability when we have a small number of trials and a small number of experiments. But as we increase the number of experiments, what we start to see is a very characteristic shape to the distribution. You can see it's changing very little. DeMoivre's theorem says that if we do a Bernoulli experiment over and over and plot the relative frequency of the proportions of heads obtained, we wind up with, believe it or not, a normal distribution with a mean of 5. If you go back and look here, if we were to increase this to 5,000, you can see a nice normal distribution. Now you might say, well, why are there voids in here? And that's because you can only have tenths in this particular option with 10 trials. If we were to change this to 15, we would actually get even a broader and more normal distribution. There's some voids in there. If we were to change this to 25, let's say, and do it 5,000 times, what we'd see is something that's very, very close to a normal distribution. If we were to do it again, we would see this distribution changes very little. So DeMoivre's theorem is that the relative frequencies of the relative frequencies, or the proportions of the proportions of heads, will be a normal distribution with a mean of 0.5. And hopefully we illustrated that in Excel. So this leads us to this problem. When we talk about flipping a coin, we think of it as a random event. But what does random mean? It means that it's unpredictable, yes. It also means random events are also ones that are independent, or they forget, and that is future events are not influenced by previous events. When a coin is flipped, it forgets what happened last time. And this leads us to the paradox of randomness, because if random events are unpredictable, why do we see results consistent with Bernoulli and DeMoivre's theorems? How can the outcomes of a random process be orderly? And the answer to this question is sometimes what we refer to as the latent order of random events, and that is, even though we cannot predict a single outcome, we can predict a larger outcome, meaning a larger group of singles, if you will. Even though I can't predict how many heads are going to come up, whether a head will come up on a flip of a coin. I can tell you with pretty good likelihood how many heads you'll get upon 100 flips. I have much better accuracy predicting the outcome of 100 flips than one. So this leads us to random sampling, which is a process whereby each observation in the population has an equal chance of being included in the sample. And there's a number of ways to randomly sample. You can put slips of paper in a hat, or marbles in a jar. You can use a random number table. You can use a random number generator in Excel, like I have here. So even though what we see is the event-to-event probabilities, or the event-to-event predictions, are difficult to make, it's much easier to make a prediction about a larger group of random outcomes. That's why random sampling is important. There's two types of random sampling. We call random sampling with replacement and random sampling without replacement. Independent random sampling is after choosing, each selection is replaced. Random sampling without replacement, or dependent random sampling, is after choosing, the selection remains out. It is not replaced. This obviously violates the concept of independence, and we wonder if we should consider it random. This leads us to sampling distributions, and that is when we take Bernoulli, we take DeMoivre, we take random samples, we put them together, what we wind up with is what we call sampling distributions. A sampling distribution is the probability distribution of a statistic computed from all possible random samples using the same sample size from the sample population. This is a critical issue. It shows us the outcomes of a possible set of outcomes from an experiment. So let's break this down. What is a sampling distribution? It's a sample. It involves samples, which are subsets of scores. The number of observations in a sample is equal to n. A random sample is one in which each observation has an equal chance of being included. It is a distribution of a statistic. That's a quantitative characteristic of a sample, like a mean or variance or standard deviation. And it is the probability distribution of that statistic that represents scores and the likelihood of their occurrence graphically or in tables or something like that. Sampling distributions show the likelihood of obtaining a value of some statistic given n observations. So for example, if we wanted to know the probability of getting a mean of 4 with 3 observations, we would construct a sampling distribution based on that. That's the usefulness of sampling distributions. We're going to talk a little bit more about them in the next few videos. Thanks for listening.